We've been talking quite a bit over the last week about how to find the limit of a function as it approaches a specific x value. Many times we've been talking about how if the graph is continuous at that point, then the limit exists. What we're going to do today is really dive into the definition of continuity and how to tell when a function is continuous, how to prove it, and also how to prove that a function is not continuous at a specific x value. So previously when we talked about whether or not a function was continuous, we said that the function would continue without any gaps or breaks in the function. And we talked about how you could basically trace the graph without lifting your pen or pencil. Now, to really understand what it means for a function to be continuous, we have to take a look at what it means for a function not to be continuous. Now, there are three different ways we have seen discontinuity so far. The first is a jump discontinuity. The second is a point of discontinuity. And the third is an infinite discontinuity. To really clarify the difference between the two, I'm just going to draw a quick graph. So let's say I had my graph and everything was going along fine. I have an upside down absolute value graph. Let's say I have an open circle. And then I have to jump down here to connect with the next piece of my graph. If that were to happen, then at this point I have what's called a jump discontinuity, because I literally jump from one piece to the next. A point discontinuity would be, let's say I have a parabola here, and then I have an open circle, and then my graph shoots up like that. This right here is a point discontinuity because there is literally a piece of my graph missing. Now the last discontinuity is an infinite discontinuity, and what this looks like is, let's say we have a rational function, and it's doing one of these, okay? Right here at my x value of my vertical asymptote, there is an infinite discontinuity. Even if the two branches of the asymptote are going the same way and the limit exists, there is still an infinite discontinuity. So then the question becomes, well, how do we prove a function is or is not continuous at a specific point, especially if we don't have a graph to look at? So let's take a look at that definition. Okay, when we are asked to prove that a function is continuous at a point x equals a, there are three steps that we have to follow. While this may seem a little tedious, this is required. It is necessary to show these three steps. Alright, so first we have to prove that the limit exists at the given x value. Depending upon the problem, you might have to do several steps just to show this. Remember that in order to show that the limit exists, we have to prove that both the left and the right limits are equal. So as you can see, this does involve some additional steps. Secondly, we have to show that the function is defined. There are many times when the limit exists, but the function is not defined there. That could happen because there is a hole in the graph or an asymptote. And then thirdly, we have to show that not only does the limit exist and the function is defined, but they're actually meeting at the same spot, and that's what step 3 does. As you go through this process of proving a function is continuous, if at any point the proof stops working, then that's when you would say the function is not continuous. Okay, so to prove that a function is not continuous, there are a couple different ways that we can do this. You don't have to show every way that it doesn't work, but you have to clearly state one reason. And basically, you're going to refute one of each of these points up here. So the way that you could show that step 1 doesn't work is you could show that the limit as x approaches the a value of the function does not exist. If you can prove this, then the function is not continuous at that x value. You could also show that the function value of a is not defined, and it could not be defined for many reasons. You don't have to explain why, you just have to say that it is not defined. And then lastly, you could go through steps 1 and 2, and it's possible that they don't give you the same value. So in that case, the limit as x approaches a of f of x would not equal the function value at a. So you only have to show one of these. You do not have to show all of them. And for some functions, more than one reason will work, okay? You cannot say things like, it has a jump. Okay, that's not good enough. That's not using a mathematical explanation. We have to use one of these three reasons, basically showing one of the three steps to prove it does not work. Okay, for the part 1, example 1, I want you to look at the graph and determine where the function g of x is not continuous and state what type of discontinuity it is. Here, when I ask you to give a type of discontinuity, I'm looking for words like jump, point, or infinite. Alright, pause the video and answer these questions. Okay, hopefully you got the three different discontinuities occur at x equals -1, x equals 0, and x equals 2. We can see at x equals -1 there's a clear jump in the graph. If you were tracing this with your pencil and you got to here, you would literally have to pick it up and jump on down to another piece to continue tracing. When we approach x equals 0, we can see from the left that we are going up, 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 up to positive infinity, and then from the right we are going down, 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 down to negative infinity. Even if these were both approaching positive or both approaching negative infinity, it would still be discontinuity. It would still be discontinuous there. And then thirdly, at x equals 2, there is a clear hole in the graph, so that is your point discontinuity. When we label intervals where the function is continuous, it's important to remember that we just said that the graph is not continuous at x equals -1, 0, and 2. So even though we see solid circles for some of those values, we cannot put a bracket there because we've already said the function is not continuous there. So when we list off our intervals, we can start, it looks like the graph counts by half units. So we can start with -3.5 is where the graph begins. Then it is discontinuous at -1, so we're going to do comma -1 with a parenthesis, union, again, -1 with a parenthesis, to 0, 0 to 2, and then 2 to 3. It is okay to have brackets on the beginning and ending of the intervals if there are solid circles. We cannot, however, use brackets on the middle of the intervals because we are stating that the function is not continuous, and if it's not continuous, it would make no sense to include a bracket saying that that value was included on the intervals of continuity. Alright, so now when we get to these bottom questions where we are explaining why it is not continuous, we cannot use the language that we used up here in part 1. The words jump, infinite, and point are used to label the type of continuity. When I want to explain why it is not continuous, now I need to use the definition that we started the lesson with. So if we think about those three reasons that we had, the first was that the limit does not exist. The second was that the function value is undefined. And the third was that the limit and the function value at that x value were not equal. Okay, so if we look at -1, at -1 we have a jump discontinuity. And whenever we see a jump discontinuity, the graph does not approach the same value from the left and from the right. So what we can say here is that the limit as x approaches -1 of g of x does not exist. From the left and from the right we approach different values, therefore the limit doesn't exist. When we look at part 4, we're trying to answer why it's not continuous at x equals 2. Now if we look at the graph here, we can see that the limit of the function is approaching 1, and the function value is 1.5. Since those are not equal, we can say that the limit as x approaches 2 of g of x is not equal to g of 2. Now notice that my notation is specific. I am putting in the correct x values to show that in this case I found the limit and it was actually equal to, what did we say, 1.5? And it was actually equal to 1, and the function value, which was 1.5, was not the same, therefore the limit didn't exist. Now when we look at the x value of -2, we can see there that the function is continuous. When we look at it, we can see that from the left and right the limit exists, the function is defined, and we can also see that the limit of the function is approaching the function value. So now, when we go to explain it's continuous, we've got to lay out this three-step proof. So first, we have to address whether or not the limit exists. Now, in order to address if the limit exists, we have to find the limit from the left and the limit from the right. So we could say that the limit as x approaches -2 from the left is equal to the limit as x approaches -2 from the right. So the limit as x approaches -2, the function g of x, exists. So we've taken care of our first criteria. Now we look at our second criteria. Second criteria is just seeing if the function is defined. So at the x value of -2, g of -2 is equal to 0. So the function is defined. Lastly, we have to show that they are equal. And in our first part, the limit does exist and it equals 0. So for part 3, we can say that the limit as x approaches -2 of g of x is equal to g of -2. Therefore, and these three little dots are a symbol for therefore. So therefore, g of x is continuous at x equals -2. Now when we are asked to determine if the function is continuous from an equation, we are still going to approach the problem the same way that we did from the graph. The only difference is the way that we evaluate the limit. We have to plug it into the piecewise equation. So first, to determine if our graph is, if the limit exists, we need to find our left and our right-hand limit at x equals 1. So for part 1, we'll say the limit as x approaches 1 from the left of f of x, coming in from the left, would be x values less than 1. So I would use this top equation. So that would equal -2 times 1 plus 3, which equals +1. The limit as x approaches 1 from the right of f of x. Now I would use the bottom equation, equals 1 squared, which is also 1. So both of these show us that the limit as x approaches 1 overall for f of x equals 1. Part 2, I need to find the function value. When x equals 1, that is right here because of the symbol. So f of 1 would equal 1. And because both of these are the same, then we can say that the limit exists. So step 3, we would say the limit as x approaches 1 of f of x is equal to 1, which is also equal to f of 1. Therefore, the function is continuous at x equals 1. And your own style of doing this proof will be probably slightly different from mine, but the key component is that you show all three of these steps. And to make it easier on everybody, please label them 1, 2, 3. Alright, so part 7. Determine if the function is continuous. Explain your answer using definition of continuity. Alright, so basically that means whenever you see definition of continuity, that means you have to show all three steps. Alright, right now we're working with a rational function, and things that we should understand are that rational functions can be discontinuous if we have a point of discontinuity, which occurs when we cancel off a factor, or if we have a infinite discontinuity, which occurs at a vertical asymptote. Either way, we're going to have to go ahead and factor this function. Alright, so if we factor this function, the denominator is easy to factor, x plus 5, x minus 2. And once we get this denominator factored, typically a lot of people will use that to help solve the numerator. And looking at the numerator, I'm going to start with the factor of x minus 2, and then I will try 3x minus 2 and see if that gets the job done. And that does go ahead and factor to what our numerator was. Okay, so based off of that, I can cross off these x minus 2's. Now, when a factor completely cancels, that's where we see a point of discontinuity. So what I can say here is I can say that g of x is not continuous at x equals 2 because, and here's the key thing, you cannot say there is a point discontinuity. That's not allowed. Instead, what you need to do is say what that means. So, okay, there is a point discontinuity, but why is that special? What does that mean? Well, if there is a point of discontinuity, that means that the graph is undefined there. So we would say that g is not continuous there because g of 2 is undefined. Okay? Now, the other area where I'm going to have a discontinuity will come from the factor that still remains in my denominator. So here, I can say that g of x is not continuous at x equals -5, and there's actually two reasons that I can give here. The first reason, which is the most common, is that the limit does not exist. So it's not continuous at x equals -5 because the limit as x approaches -5 of g of x does not exist. Now you could also say because g of -5 is undefined. So when we happen to have a vertical asymptote, a couple things happen. First of all, the graph has an infinite discontinuity. Second of all, it is undefined there. So when you give your reasonings as to why it's not continuous, you have to be specific with reasons related to the definition of continuity. Okay, in this last section of the notes, now we are asked to find the value of a such that the function is continuous. So if we think about this, in order for the function to be continuous, then the limit has to exist, meaning the left and right limits must be equal at that specific x value, and the function has to be defined, and those values have to equal each other. Alright, so if we start with that first reasoning, that the limit from the left has to equal the limit from the right, then we can go ahead and we can set the left and right sides equal when x equals 2. Okay, so we're going to go ahead and we're going to say that 9 minus x squared equals ax when x equals 2, and then we're going to plug 2 in for x, giving me 9 minus 4 is 5 equals 2a, and if we divide by 2, we get that a equals 5/2. Now from here, we're going to go ahead and we're going to walk through the proof just to verify that we are in fact continuous. So part 1, the limit as x approaches 2 from the left of h of x, if we plug in 5/2, we will get the limit as x approaches 2 from the right. Okay, if we plug 5/2 into each of those, from the left we end up getting 5, and from the right we end up getting 5. So that's true. Step 2, we want to find the function value. So h of 2 would equal 5/2 times 2, which is equal to 5. And so then step 3 works for us. The limit as x approaches 2 of the function is equal to the function value of 2. Sorry, this handwriting is so atrocious in this note-taking app. Doing the best I can. Alright, if we look at the next problem, in the next problem we happen to have a rational function. So if we were to go ahead and factor this numerator, that would give me x plus a, x minus a, over x minus a. And we know that these x minus a's are going to cancel, so that means that the function is just going to look like x plus a. However, there will be a hole or a point of discontinuity. So there's going to be a hole or a point of discontinuity at x equals a. So basically what's going on here is that this top part of the function is everything but the hole. And then this bottom part of the function is the hole. So in order for this function to be continuous, whatever value for a I give basically has to plug the hole. So if this were my rational function, and let's say it was going like this, and there was my hole in the graph, Sometimes we'll see the points down here. Sometimes we'll see the points up there. Well, in order for this function to be continuous, that point that plugs the hole has to be right there. So that's what we're trying to figure out right now. So what we're essentially saying is that the limit as x approaches a of the reduced function x plus a would have to be equal to the function value at a. And the function value at a is equal to 8. And we know that because of this right here. Alright, so that's where we're at right now. We know that the limit exists for the function as x approaches a because we know that it's going to look like a line with a hole. And we know based on this part that's circled in blue that the hole actually has a value. The question is if the hole that is provided on the red graph is filled in by the point that we have defined. Alright, so in order to solve for this, we need to actually solve this limit on the left. And to solve the limit on the left, we would plug the a value in. So we would say that if we plug a in, a plus a has to equal the function value, and the function value at a is equal to 8, and we have that right here. So 2a equals 8, which means that a would have to equal 4. So basically what this is telling me is that if a is equal to 4, then when I have the function given by x squared minus a squared over x minus a, when given that function, that the hole provided would be plugged in with this hole that's given right there. Alright, tonight's homework is worksheet 7. We will recap this tomorrow and then prepare and study for our test. Have a nice day.